Thanks for joining this session. My name is Marit Zöcklein from the Center Construction Robotics in Aachen, and with me here is Manuel Pitz from the Ion Energy Research Center, also based in Aachen. And on behalf of our co-authors, we present you how we can enable energy monitoring for construction sites and also in robotics environments. So in the last few days and also last week at LDAC, we've heard a lot about energy monitoring in buildings and learned about all the analysis we can do, like for predictive maintenance and also for KPI assessment. And then only yesterday afternoon, one of the presenters mentioned, yeah, when we speak about energy consumptions, when we speak about emissions that are related to that and generated, and maybe even ESG reporting, so maybe let's not forget about the construction side and all the activities that are going on there. But then, I mean, it's only valid to ask, so how do you think we can keep track of all the consumers in such a chaotic, unstructured environment as we see here? And I mean, this is a small-scale construction project. Yeah, you're totally right to assume that it's super challenging. And we looked at our small test bed in Aachen, where we only have a handful of machines, a tower crane, maybe a robot, and some other devices who are consumers. And in the end, we were not even there able to distinguish all their different power consumptions because they shared the same power access box, and then the connection from this box to the grid was the one that counted. While we were not able to come up with a solution for that ourselves, we were yet able to define a set of criteria how the solution should look like to be usable in practice on site. And first of all, ideally, it wouldn't require a certified electrician because thinking of that you're always under time pressure and it needs to be fast, you just cannot afford to book an appointment every time you need a process to be monitored. Then second, we are outdoors. It's dirty, it's dusty, there is solar radiation, there might be rain, so the solution would need to be quite robust. And yet, if we want normal workers to deal with it and to operate it, then it should also have a form factor that it's manageable by a human worker. And lastly, the data transfer should happen wirelessly, so dragging along a LAN or Ethernet cable is just not suitable outdoors and in other production environments.
Okay, and there I take over with the practical implementation of this hardware. So the idea here is that we have on the left side our block diagram of what we propose as hardware, and on the right side you see actually the hardware that we implemented as photos and highlighted some of the key components. So at its core we have a Raspberry Pi 4. That one is connected via USB on the one side to a USB to Modbus adapter for reading the metering data. And on the other side, we can actually connect it to a 5G modem so that we can either use the built-in Wi-Fi for local monitoring. So if you're nearby the device, you can connect with your tablet, or we can stream our data directly to a local, via a local 5G network to a cloud so that we can aggregate actually multiple of these devices. And on the bottom then we see actually the power side of this device. So we have a CE plug, and on the right side you have the CE socket. You see that also in the picture on the very bottom of it. And that is how we actually interface with our device under test. So you essentially bring the device, the Meter X device, to your device under test, being in the crane or whatever. Then you connect the power supply to the left side of this Meter X device and your device under test to the right side. So you're essentially in line. And that makes it rather easy to use. And we can essentially roll it around on the construction site via these small rollers, like a small trolley. You can just pull it around. And with the casing that we designed for it, or that we are using here, we actually have also the weatherproofing, and we can run it outdoors. We tested it with hosing it, and nothing bad happened, so that should be quite okay when it comes to bad weather. Yeah, let's go to the next part. So I already started to talk about this metering device. So we are using off-the-shelf hardware for that. That's the ABB B23 three-phase meter device. You see it here on the bottom. That's a picture of it. And based on the data sheet, it has an accuracy of around 1%. And we also, of course, wanted to understand if that is really the case. And we tested it with two types of loads. We tested it with a symmetric load and with an asymmetric load. The symmetric load, we went up to 4.5 kilowatt of the up to 43 kilowatt that the device can actually measure. And for the asymmetric load, we went up to 6.8. Right now, we only have a picture of the asymmetric one because that has the worst results. The other one you find in the paper if you're interested. And one maybe important point here is that these devices are essentially designed for symmetric loads. So symmetric loads happen when you have a motor or any big hardware that actually needs a lot of power. Then you have actually quite symmetric loading of the system. And asymmetric load happens if you have a single phase connection only. Let's say you have a heater or something like a big drill that you want to connect. And there we see the testing here was done with an LMG671. This is a precision power analyzer that we connected in parallel to this metering device to actually measure at the same time the load from both devices. And there you can see that the error goes slightly up. And in the envelope, you see actually the error envelope that is introduced by the LMG671. Coming to the next one, which is now kind of the use cases that we tested. So we tested 2 use cases, one on the construction side and one in the robotics with a robot arm. Here you see the device connected to a Kedar material lift that we then use or that we then ascend and descend again, empty. And you see that we have all the 3 phases here, and the 3 phases are, as we expect, quite symmetric. And one thing that is worth mentioning, that our lowest power is actually minus 200 watts. So this one is a motor that is directly connected to the grid. When we go downwards, we actually feed in. So there is no variable frequency control in between. Then the maximum power that we see is somewhere around 1.2 kilowatt. And the interesting thing here is that our power consumption, not interesting, but to expect it, the current power consumption stays essentially the same when we are going upwards. And the peak power when we are descending is actually quite interesting because we have to somehow unlock the device. Coming to the second use case, which is an evaluation of our robot arm. In this case, we have a single phase load, which you see here on the left side. This robot arm is moving around a fixture with weights from the left to the right of the table. And we can change the amount of weight. You see the fixture in the lower left corner here. And what we did is we had it fully loaded with 4 weights and did 4 cycles. Then we unloaded it without any weights and did another 4 cycles. You see the result here. What we can again see that is we can clearly see the peak power, and we see the increase in power when we go higher weights. And what is actually interesting, or what is very interesting here, is we use exactly the same device. So we use the same device for construction testing and the same device for very low power consumption. So here in this case, 30 to 60 watt. And we can also already see some implications about the trajectory in this power consumption. This brings me already to the last slide, our conclusion. So what we showcased was the deployment of a plug-and-play solution for consumption measurement on the power on the construction side. We evaluated the used metering device and tested for its accuracy, and then we executed measurements on 2 different use cases, on the construction and in the robotics. And finally, we analyzed the consumption pattern and checked if we can actually get any insights of these consumption patterns. A couple of things that we would like to do as future work is more real-time analytics. So up until now, we essentially did this measurement campaign, and we downloaded the data, and then we analyzed it. And one example for real-time analytics you see here on the upper right side, which is detecting patterns in our power consumption, and all of these vertical lines are actually patterns that we detected. Okay, then what else do we want to do? We would like to use this measurement device for actually doing something like predictive maintenance or process planning. That is something where we have to look at it more into detail when it comes to having more data sets. So if we want to do predictive maintenance, we need long-term measurements. And finally, something like CO2 equivalence, that's part of the Target X project. And you see some of the measurements that we also did after we started with the paper, or we did the paper here on the lower right side, where we measured actually different weights on the lifter. And last but not least, one idea that we have is also consumer-specific billing. So if you share this lifter device, what you could do is actually establish based on this measurement who is using it, when and how much. So how much weight did they actually put in it? How much power did it actually consume? And with that, we essentially close with 2 pictures. So on the left side, you see the Grafana dashboard that you are greeted with when you log into the device. This is essentially the current user interface, very simple. and then again the construction site. Thank you very much, and now we are open for questions.